Hello, everybody. So I thank you to organizer for a very nice conference. And my report will be dedicated to the following question about topologization of some algebraic structure. The first, sorry, so some definition. So I know that you well know such definition from the calculus or general topology when map is left continuous or right continuous and separately continuous if this map is both right continuous and left continuous. Jointly continuous if it is continuous between the product and x and y to the space x, yeah. And in the theory of topological semigroups, the following definition are used. Right topological semigroup if the multiplication is right continuous, it's equivalent that all left shifts are continuous map and dual by left topological semigroup. A semi-topological semigroup if the semigroup operation is separately continuous. And a topological semigroup if the semigroup operation is jointly continuous. So later, a topology on semigroup S is called semigroup topology if S with this topology is topological semigroup. Shift continuous is if in case S tau is semi-topological semigroup, and left continuous topology if this semigroup is left topological semigroup. Yes, by dual we get the right continuous topology. So the first result about topologization in topological algebra was obtained by very nice result by Leo Pontryagin, who gave well-known 5 conditions of the topologization on at the unity of the group for non-discrete topologization. Yeah, and after Pontryagin, Marco in 1945 posed the following equation about non-discrete Hausdorff topologization of group. Yeah. And this Markov equation was refined by the following equations. Can a given infinite group G endowed with a non-discrete group topology be embedded into compact topological group? Again, for the arbitrary abelian group G, the answer is an affirmative, but there is an non-abelian topological group that cannot be embedded in any compact topological group. So also maybe 15 years ago, we proved that some group does not embed in a compact topological semigroup. Yeah. So the first answer, first counterexample on Markov equation was counterexample, Olshansky counterexample. Olshansky constructed an infinite countable group G such that every Hausdorff topology on G is discrete. So, but before Olshansky, Kazakh mathematician, academician Timanov presented a commutative semigroup T with which admits only the discrete Hausdorff semigroup topology. And after that, he gave a sufficient condition on a commutative semigroup to have a non-discrete semigroup topology. So, for topology, for groups, for case of group, as Eugen Zelenyuk, well-known Kyiv and South Africa mathematician, proves that on every countable group there exists a non-discrete regular topology with continuous shifts and the inverse. Also, every countable locally finite group admits a non-discrete Hausdorff topology. Also, Olshansky group constructed the first example of infinite hereditary non-topologizable groups. And my report will be devoted to the following. First, I present some non-topologizable semigroups. And next, what subsemigroup of such semigroup are not topologizable. So the first definition of Taimanov semigroups is defined by this formula, yeah, of the cardinality of 1 plus kappa, yeah. And Taimanov proves the following theorem. For any non-zero cardinal kappa, every house of semigroup topology on Taimanov semigroup T kappa is discrete. But I prove the following theorem. Let kappa be any non-zero cardinal, then the following statement holds. Every shift continuous T1 topology on Taimanov semigroup is discrete. The next, a Taimanov semigroup T kappa is closed in any square topological semigroup which contains Taimanov semigroup as a subsemigroup and satisfies the separation axiom T1. The following: any non-isomorphic homomorphic image of Taimanov semigroup is zero semigroup. This implies that every non-isomorphic homomorphic image of Taimanov semigroup admits any topology. So any topology on such semigroup is semigroup topology. Also, every non-isomorphic homomorphic image of Taimanov semigroup is topological semigroup with respect to any topology states. Yeah. Also, each Taimanov semigroup is algebraically complete in the class of square topological semigroup satisfying the separation axiom T1. In particular, the Taimanov semigroup T kappa is algebraically complete in the class of a T1 topological semigroup. And the next result, and infinite Taimanov semigroup, that is not embedded into any T1 square topological countably compact semigroup. Also, this result imply very, very nice result that any subsemigroup of Taimanov semigroup is not topologizable in the previous case, that any T1 topology in any subsemigroup of Taimanov semigroup such that the semigroup operation is square continuous, yeah, is discrete. This result is similar to the result for groups which were obtained by Olshansky group. So the next very nice result, very nice semigroup is a bicyclic semigroup. What is a bicyclic semigroup or bicyclic monoid? Is a semigroup with identity which is generated by two elements P and Q, subject only the condition P multiplied Q is equal 1. So all distinct elements of the bicyclic monoid are exhibited in the following usable infinite array, yeah, and semigroup operation on the bicyclic monoid is determined in the following way. So the first result about bicyclic semigroup is the result Eberhard Selden, and he proved that the bicyclic semigroup admits only discrete Hausdorff semigroup topology. This result was extended to semi-topological case by Bertman and West. And also we study the closure of the bicycle semigroup in any type of topological or semi-topological semigroups in the following papers. Yeah. And we consider two subsemigroup of the bicycle monoid, C plus and C minus. So it's very simple. Result that C plus and C minus are anti-isomorphic submonoid of the bicycle monoid. And some old my result about topologization. Every Hausdorff left continuous topology of the monoid C plus is discrete. Every Hausdorff right continuous topology and by dual semigroup also is discrete. And the following these two theorem is are a corollary of the following theorem that if S is infinite semigroup, if for any element S of S there exists any idempotent I S such that S belongs to S without S ES, and the set S without SES is finite, then every Hausdorff left continuous topology on the semigroup S is discrete. By dual, we get right continuous topology on dual semigroup S minus. And we get the following theorem. The monoid C plus contains the family dB plus of cardinality continuum of non-isomorphic submonoids of the semigroup C plus, so that for any element S alpha from this class, the following condition hold. First, every Hausdorff left continuous topology on S alpha is discrete. Every semigroup S alpha admits a non-discrete locally compact semigroup T1 topology. S alpha admits a shift continuous compact T1 topology. If S alpha is a dense subsemigroup of Hausdorff semi-topological semigroups T, and I is T without S alpha is a non-empty set, that I is a closed two-sided ideal of the semigroup T. The next, there exists a Hausdorff compact topological monoid which contains S alpha. Is interesting. Is very interesting result because the bicyclic semigroup does not embed into any compact Hausdorff topological semigroup. And the next, the semigroup S alpha admits a non-discrete right continuous topology which is not left continuous. So also for proof this this theorem we use it previous theorem, and the general question which we pose to us to study is the following: does there exist a semigroup S which does not satisfy the assumption of theorem 3, and every Hausdorff left continuous topology on S is discrete, or right continuous topology is on S is discrete? So we consider the set of integer z that on the Cartesian product the square, we define the semigroup operation in the following way, yeah. And the semigroup with such operation is called an extended bicyclic semigroup. This semigroup contains infinitely many isomorphic copy of the bicyclic semigroup. So the distinct element of this semigroup are exhibited in the following useful infinite array. So we consider such semigroup, yeah, and the distinct element of this semigroup we exhibit in the following array, yeah, and we get the following nice theorem: every Hausdorff left continuous topology on this semigroup is discrete. More than we prove the following theorem: the extended bicyclic semigroup CZ contains infinite the family DC of cardinality continuum of a non-isomorphic subsemigroup of the extended bicyclic semigroup, so that for any element C alpha of this class, the following condition holds. First, every Hausdorff left continuous topology on the semigroup S alpha is discrete. Second, the semigroup S alpha admits a non-discrete locally compact semigroup T1 topology. Third, there exists a Hausdorff compact topological monoid which contains S alpha. And fourth, the semigroup S alpha admits a non-discrete right continuous topology, which is not left continuous. So this is a minor result of my report. And that is all. Thank you for your attention. But the next report will be my student. He consider when subsemigroup is of the bicyclic monoid is discrete. She gave a sufficient condition, but we don't know if this condition is necessary for non-topologized this semigroup. Thank you for your attention. Дякую за увагу. Дякую мужньому Києву і київлянам. Дякую мужній Одесі і одеситам і одеситкам. Дякую усім українським містам-героям, які борються проти східної чуми. Дякую вам за увагу.